Hello and welcome back to LeetCode. We're going to look at a medium problem number 129, sum root to leaf numbers. We're going to follow an approach that where we try to verbalize what we're doing, and we're trying to do a random analysis before we write any code and all of that. This is intended for interview practice, where you're going to be judged on how well you communicate and how well you can, how you approach the problem solving, and how well you can articulate what you're doing while you're doing it, so that your interviewer doesn't wonder what is going on. Because a perfect solution isn't going to help you if you can't explain it well. So yes, so let's look into this problem. I have solved this before, over a year ago. I don't remember what the solution is, but this is, I think, a popular one that might get asked a lot, according to sources, sources being random people on the internet. But yeah, so I thought we'd just take a look at it and try to solve it again. So sum root to leaf numbers. You are given a root of a binary tree containing digits from 0 to 9 only. Each root to leaf path in the tree represents a number. For example, the root to leaf path 1, 2, 3 is the number 1, 2, 3. Root to leaf path. So I guess not in this example. Return the total sum of all root to leaf numbers. Test cases are generated so that the answer will fit within a 32-bit integer. For us, as Python users, that doesn't really matter. But people who use C or something, or Java, I think for those, that information matters. Not for us. A leaf node is defined to be a node with no children. Okay. So let's look at the constraints, as we always do, as the second step. The number of nodes in the tree is in the range of 1 to 1000. So our root will always be a node or a leaf node. We don't have to deal with the case where it's none. It's nice. For a runtime complexity analysis and space complexity analysis, we're going to ignore the fact, of course, that there's an upper bound to the number of nodes in the tree. Otherwise, everything will be constant space and constant time automatically. And another constraint is that any node in the tree has a value between 0 and 9. The depth of the tree will not exceed 10. All right. Okay, and well, one question that I have now is, what if we have a leading 0? So what if we have in the root a 0? What do we do then? So we have to return the total sum. I guess then if the root is a 0, we have to ignore it, obviously. So yeah, that's what we have to do. We have to ignore. We have to make sure that we ignore the zeros. So now let's look at the examples here. So we have a tree, root 1 and 2 leaves with the values of 2 and 3. And let's just see if we can come up with the output. So here we have 12, 1, 2, that's 12. And the other path is 13. Yeah, the sum is 25. Nice. So we always have to go, well, we have to find all paths from root to all leaves. And then in that process, build up that number on the path. And then when we reach a leaf, we have to add that number to our result. Cool. Let's just have another look at the second example. So here, so 40 is one number. Then we have the number 495 and 491. 495, 491, and 40. That sums up to that. Yeah, okay, cool. Nice. And yeah, so we could solve this iteratively, but because this is a tree problem, I would really like to do a recursive solution. So we're going to call a function recursively m times or h times, where h is the height of the tree. And we're going to ultimately iterate through all of the elements in the tree. So the runtime will be O of n, n being the total number of nodes in the tree. And the space complexity will be O of h, being the height of the tree. And for our result, we just need constant space to store the total sum, right? time and O of h space, and this number of nodes in the tree. H is height of the tree. So result, we're going to do, I like to use the variable name result for the result, just because it's so self-explanatory. Some people might say total sum or whatever. Do whatever you like. I like this. So now we need a little helper function, and I like to put them directly inside the method where we're trying to solve it. You know, you could also put it here, Sarah, if you wanted to. Up to you. I like to put them here, especially when they're very small. I think that makes a lot of sense. So you're going to put in a node. In a coding interview, I would probably not put any, how do you say, type annotations here. But you could if you wanted to. But here for this video, I'm just going to add them here. And yeah, and well, since we defined the result here, we should be able to you know, modify the result in here. Whatever we want to say. So now we said that we need to build up the number as we descend down the tree from the root on, right? And so we will start from the root. So we call the helper of the root, and then return the result. Now, there's also another way of how we could do this. For example, if you just say that the helper should actually return the result for us, right? So we don't have to use this extra variable, but then we have to return, I guess, something here. Yeah, let's try that. When you implement this yourself, you know, try both approaches. It's good to know how to do both of them, but they don't really change the outcome. And what we also want to do is we want to know what is the current path. So we need something to keep track of what are the values that we visited. And I would suggest we use an array for that. And we're going to treat this array like a stack, right? And this will be list of int values. Let me double check. Yes, we have integer values in here, so that's fine. We don't have strings or anything, so it's ints. So, well, when do we terminate? Well, when we don't have any leaf nodes, right? So if node.left is none and node.right is none, that means we've reached a leaf node. And we should return the result, right? So the first thing that we do is before we even do this check, what we do is we add the value of the current node. Let me just think about this. You know, there are two ways of how to handle detecting a leaf. You could say, well, we check if no, actually, this is the right one. We check inside whether we have left or right nodes or not. So what we do first is we're going to append to a path the node value. That's what we're going to do. And because we guaranteed that we have at least one node in our tree, that means the first one we call the helper function. This is guaranteed to exist. So we don't have node is none. And so it's not even an optional. Why? I don't understand why this one is then one. But anyways, so, and now we check whether it had leaves or not. If it doesn't have any leaves, then we need to, well, we need to construct what the number is. And what is the number? Well, so we have to iterate through all of the digits for digit in path. And our number is going to be 0. And then what we do is we do number. We're going to shift it to the right in decimal notation. And then we're going to do number cross equals digit. Right. And then we return that number in the end. Because when a leaf node, there's nothing else to do. We can return right away. So if we look at this example, the path 4, 9, 5. So we have the 4, the 9, and the 5 in that order in our little path list. This pattern, by the way, is also something that you really have to know. So first we get the 5. No, sorry, we get the 4. We multiply it by 10, that's 40. We add the 9, so that's 49. So we multiply 49 then by 10, so it's 490. And we add the 5, so it's 495, which is exactly this value. So then we return this number from the leaf to the node. Now, if we have a left or a right node, let me just say, result is equal to 0 here. You know, we have to go down the left or the right tree or both, depending on if they exist or not. So we have to keep track of the results that we get back from when we call this function recursively. And here I just called it number. And maybe we should call it here sum. Sum equals 0, and then we do the check if node.left. That means we have the left node, and we're just going to add whatever results we get by summing all of the path sums when we go down into the left node from here on. So we're going to call the helper method here, helper node.left and path. And we already added that value to the path, so we're good to go. And the same here. Oh, I made one mistake here, by the way, that I'm going to fix in a second. We also need to remove elements from our path again. And I overlooked that. So now we're checking here for the right path. If it exists, we go down there and we update our sum. And now finally, when we exit the node again, we're going to remove the value. So if we exit this node, we're going to remove 5 from our path. And then the function that called us will call the right. We'll call the right, what do you call it? The helper method on the right child of 9. So then 1 gets added. So it's 491 then. So we have to take care that we actually pop the element out before we return with the sum. And yeah, so, and we also have to do this here. So to clean up the code a little bit, I'm just gonna have the sum 0. And let's see. I'm going to do the following. Since we have sum is 0, we'll just do this. How about that? So what we have now is, if we don't have a left node, oops, sorry, that is wrong. We have to keep it like this. If we don't have a left and we don't have a right node, this part executes. And it's guaranteed that we don't execute the other two. We start with the sum 0, and at the end we return the sum. But we also make sure that we pop the last, the node value out of our path again, because the path is used by all of the methods. We're not copying the list, we're just passing the pointer to the list, which shares us, of course, space. And we remain with an over H space using that. Yes, and let's see. Yeah, I think that should be it. Right? And we also gracefully taking care of leading zeros, because if the first digit is 0 here, what we'll have is we're adding 0 to it, so it doesn't really change the sum. So if this was 0 and we reach this leaf, then we would have 0, 2 inside the list, and the sum would be 2 here as well. Okay, so I think that is everything. I'm just going to check one more time, is everything correct? So if left node is none and right node, node right is none, then we do this. If they're not none, then we execute this on the left node. The right is not none, we execute this on the right, we pass on the path. Yeah, so I think that is complete. Let's run this quickly. See if it passes the test cases, and it does. And I feel confident that now if we submit it, it will also be accepted. Yes, so that's great. I don't think there's a way to optimize that one further, because we are not dealing with a search tree or anything. We have no information about, you know, the order of the nodes or any such thing. So, and we always need to build up the numbers, which means we always need at least O of H space to build up those numbers due to the recursive call. And if we were to do this iteratively, that would just mean that we have to keep track of the path that we came to be able to unwind the path again. Otherwise, we couldn't be in O of N time. So there's probably another way to do that with O of 1 space, but then at the cost of the runtime, right? But I don't know if that is even feasible, because you would have to remember which paths you already went down, which ones you didn't, etc., etc. So yeah, I think we found an optimal solution, and I recommend to code this yourself. And yeah, try to keep your code clean and simple and easy to understand. Don't be afraid to change the naming of variables along the way. If it helps with clarity, I think it's going to be good for you in an interview.